questions while we're waiting or before we start? I heard some very lively discussion about the NBC design pattern. The trouble with the NBC design pattern is the name. The name is weird. That's what I think. We're going to talk about that today, actually. So no questions before we start. I'm picking up a signal. I'm picking up a signal using my telepathic powers. Some of you have a question that you're too afraid to ask, but you're still wondering. Somebody's wondering, oh, is he going to give away leftover Halloween candy today? Who was wondering that? Bam. Yes, I still have. Let's see if we can get rid of it today. Let's see if we can find the. Who's here yet? Who else? Somebody ready? Okay, let's finish up protocols. Protocols represent this transition from design to implementation. We talked about these two web servers designs last time. We defined what a protocol is and how protocols force us or encourage us to refine our responsibilities. We talked about how to choose method names. We looked at an example from the drawing editor, and then we started looking at the guidelines for protocols, like make them general, for example, defining reasonable defaults. Now you're all thinking about how important default values are. And then we talked about the default values for this example in the drawing editor. And we looked at this parameter specification in default values in our drawing editor example again. And I think this is where we left off. Does anybody remember? I think that's where we left off. We looked at these, and I think we maybe mentioned this idea of instead of having a constructor or a method that has 4 different input parameters, we talked about the idea of using accessor methods to set those values instead, right? That's a much easier or more developer-friendly approach than trying to require 4 parameters in a method. I know that when I'm programming in Java, I'm always looking at the Java API to find the version of the method with the fewest input parameters that I can use. Does anybody else do that besides me? Am I the only one? I knew I was odd. Right, so, and then if we have these accessor methods, then we have to figure out where to put them, right? And they should go in the appropriate class, right? Whichever class handles that data, like there might be a device class, there might be a color class, you know, and so on. Okay, and then these last few slides are just what happens when you define all the protocols. Like, what are the final stages of your documentation, your design documentation, actually. It's very complicated. If you follow all the rules really strictly, you find out that you have this long, very long and complicated design document at the end. So the result of defining these protocols might result in some alterations to the hierarchy and collaboration graphs, right? Because you've refined the responsibilities. The responsibilities might have been updated. And it would be nice to have a single system, like a single page with the system overview, including the subsystems, including hierarchy roots, as an overview diagram. And then if you have subsystems in the overview diagram, have those subsystems documented on separate pages, separate subsequent pages. Every class is actually given its own page, right, with the class name and the full class card. And this is what the full class design documentation actually records: the name of the class, if it's abstract or concrete, the immediate parent and child classes, so one level above and one level below, references to any graphs that it's involved in, a description of the class's purpose or its intended use, each collaboration that it's involved in, and then the list of responsibilities that it supports. Now, number 7, actually, I could delete that. We're not generally concerned with private member variables, private methods, private responsibilities. However, if you want to speculate on the use of those, it's fine. And then possibly something about the implementation, like what kind of error messages, performance requirements, etc. The subsystem specification is almost identical, right? Because subsystems can just be abstract classes. And then we have a set of diagrams, the set of descriptions for each class, the set of descriptions for each subsystem, and that's basically it. There is one thing I didn't mention, and I'm a little bit disappointed. Does anybody know what I forgot to talk about? That I don't know why I don't have a slide on that topic. There should be a slide. It's like it disappeared somehow. I missed this topic. Anybody know what it is in the protocols? Does anybody know what the 3 parts? A protocol consists of 3 parts. Does anybody know what those parts are? Can anybody answer that question? That's a basic question. Nobody wants to try to give that an answer? A protocol consists of 3 parts. What are those parts named? Say it again.
Just give me a name.
What do you think?
Would like timing be one of them?
The 3 parts. So a protocol consists of 3 parts, 3 components, or 3 aspects. What are they? Okay, I guess I should have that as a test question. It's an easy question, but if nobody knows the answer, it sounds like I should have it as a test question. Any guesses? We talked about 2 of the parts in this last lecture on protocols, right? But I missed a part by accident. Nobody wants to guess. I guess everybody's sleeping. The parts are method names, right? We talked about method names. Input parameters, we talked about input parameters. And the third part, anyone? Nobody? Name? Philip.
Maybe like a return value.
Return values, yay! It's too dangerous to throw that one, I think. Congratulations. Yes, I did talk about return values. And I don't know why I don't have a slide for that. I should have a slide for that. Hopefully next time I will. Anybody think about return values at all? You can tell how good somebody is as a developer just by looking at their return values. No, it's a piece of evidence. So there is a problem here because people don't think about return values actually by default. By default, I don't know, the default value that everybody chooses for a return value is void. Right? Oh, I don't want to think about that. I'll just return void. Right? That's what everybody does. That's actually bad practice. That's poor practice. Anybody have any idea why? It's a lost opportunity. Right? The methods always have a return value. So even if you return void, there's going to be a message that returns a void from a method. It's a lost opportunity. Can anybody think of a better default rule than just returning void in a method? Has anybody ever wondered this? Name?
Maximilian.
Maximilian?
Yeah.
Not really.
You can return 0 or 1 to indicate whether you succeeded.
Yes, that's right. So return true or false. Return Boolean. If the method successfully finished, you return true. If the method did not finish properly or as expected, you return false. That way you can always check if the method succeeded or not. Right? Imagine you have a method called save file. That's not the world's best example, but as a hypothetical example, you have a method called save file. You don't want to return void. You want to return true if the file save worked, or false if it didn't. That's the default return value. Even if you're always returning true as a default value, that's better than returning void, because you can in the future versions of that method, you can update it to return true or false, like success or failure. So that's one thing I didn't mention that really deserves a slide. So think about that. If you see people writing their methods with lots of just return voids, that's a sign. It's a sign of somebody who's not thinking about their return values, and it's not good. Name? Polka.
That's where you use exception in Java. Why do we need to return Boolean? Why?
Yes, that's why I didn't. I said that was a bad example of the fun. So if there's an exception, then that's not true. Like the save file example is going to throw an exception in Java. That's why it's not the world's best example. But you can imagine any method that doesn't throw an exception returning true or false. Does that address that question, hopefully? Yeah. Good question, good observation, by the way. Any other questions about protocols? I see tests. I'm dreaming of test questions. Okay, good. So we'll stop the lecture on protocols and start the lecture on design patterns. Actually, that's a kind of a good transition. That question in design patterns. Can anybody explain what exceptions are for in Java? Anybody want to try to do that in their own words? Name?
Daniel.
Daniel.
So when something goes wrong, it's about like handling that instead of having the program crash.
Yes, that's right, Daniel. And so exceptions, if I understood Daniel's answer, exception handling is about continuing the program and making sure it doesn't crash and handling whatever error has arisen, as opposed to just crashing. And that's exactly right. But there's a kind of special quality about methods that throw exceptions, right? Not all methods throw exceptions, right? A certain subset of methods throw exceptions. Did anybody notice that? Like, oh dang, this is a method that throws an exception. I have to handle it. Like, what is that subset of methods that throws an exception? So exceptions, that's a very tricky question. That would be a good test question too. And that would be a good job interview question. It's not an easy question, by the way, at least if you're hearing it for the first time. It's dedicated to a special set of highly probable circumstances, right? For example, in the save file example, there's a very distinct and high probability that something will go wrong when saving a file. So, for example, you run out of disk space, right? Or you don't have permission to save that file. Your operating system says, no way, you don't have permission to save a file in that folder. Or you don't have a permission to save a file because that name is already used, or something like that. There's a very highly anticipated set of problems that could happen. And for those methods, Java says, okay, we know that these problems are coming, and there's a high likelihood that they are coming because they're so common. Therefore, we're gonna force everybody to handle these situations with an exception. Right? It's not for all methods. It's for special methods where we know that the probability is high that there's going to be an error. Right? It would be quite a lot of work if every single method threw an exception and had to have an exception handler. Right? That would be. But this is designated for areas where we know that a lot of errors can come already. And why am I talking about that? It's a kind of error handling pattern, exceptions. Right? It's a methodology and a pattern by which we handle errors, highly anticipated errors that occur very commonly. And why am I saying that? It's because software design patterns are very similar in conceptually, in the sense that they offer solutions, software design solutions to highly probable and highly anticipated applications. Software scenarios and software designs that occur very frequently over and over again. They occur so frequently and over again that they've given it a special pattern. We've designed special patterns to provide or guide solutions to these common problems. So that's the overlap with exceptions. I hope that made sense. And there are lots of books on this topic. I think this is the classic book on design patterns. Everybody know about freetechbooks.com? So freetechbooks.com has millions of free software engineering books. So what is a design pattern? A solution, a set of objects and collaborations that addresses problems which occur over and over again, and then describe or prescribe the solution or a solution, a generic solution to that problem, in such a way that we can use the pattern over and over again. A pattern provides an abstract description of a design problem and how a general arrangement of elements solves it to objects. A design pattern identifies the participating classes and instances, their roles and collaborations, and the distribution of responsibilities. There's a lot of overlap between the general object-oriented methodology that as applies to classes, objects, responsibilities, and subsystems with design patterns. A pattern specification has 4 essential elements. The name of the pattern, which is very confusing sometimes. I find the names of the patterns confusing sometimes, like the MVC one, for example. So if you find it some of the names confusing, you're not alone. Then the problem that it solves, the prescribed solution, and maybe some consequences to that solution for that solution. If you take a step back and you think about software, most software applications that have a human user, right? Not all software has a human user, but a lot of software has a human user. I don't know what percentage of that is, maybe 90% or 80% of all software has a human user. If you really step back and just conduct a kind of thought experiment, there's a pattern to all those software applications. They all have 4 components to them over and over and over again, and we've seen it already. Anybody want to take a guess what every kind of the basic 4 components of all user human-centered software have? Any guesses? Class is very silent today. If you take a step back, right? So the first component is going to be the user interface, right? All human-centered applications are going to have a human interface, right? That's a very common pattern. It's going to be there for all the human-centered software. Any other parts that are always going to be there, or subsystems? There's almost, is it Emily?
Yeah. Input handling, mouse and keyboard.
Oh, sorry about that. That was a bad throw. So mouse and keyboard would, yes. I would put that in the same subsystem as the GUI, like all the user input options, let's say. So mouse is a user input option, keyboard's a user input option, and then buttons on the screen. Any other subsystems that are going to be prevalent in almost all applications? There's going to be other parts, right? The data, access to the data. That's going to be a part of every single piece of software. It's either going to be a database, a file, a network, right? There's going to be some data interface, right, in every single application. You want to separate the data, right? The data access as a subsystem in your application. This is a good test question, apparently. And there are 2 more components that are just ubiquitous. Anybody want to take a guess? Processing. Another component is going to be processing. You take the user input, you're doing something with it, you're processing it somehow. Probably you're getting some data and processing that data somehow. So there's a processing logic to every program. Right? You have the user input subsystem, the data access subsystem, the processing subsystem, what the program is actually supposed to do. Like a drawing editor, for example, it's supposed to create drawings. That's the processing subsystem. But you need a place to store the drawings, right? Data subsystem. And then there's one more. Anyone? Bueller? Anybody see Bueller's Bueller's Day Off? Where the teacher says, Bueller. That's probably too old of a movie. Anyone? Fourth subsystem found in basically every single application. I'm glad we're having this discussion because this is a good thing to know and a good thing to understand and a good thing to be able to abstract in your mind. Is your hand up?
Yeah.
What's your name?
Daniel,
Daniel.
output.
Yes, the output. So you have input, data access, processing, and output. Thank you, Daniel. That's it. You're going to have those 4 subsystems in pretty much every user-centered piece of software. Right. No, I'm not talking about software where there's no human user, right? Because there's a lot of software where there is no human user. So keep that. That's like the world's most generic design pattern. It doesn't really have a name. I should give it a name, but really I should have a slide just for that generic pattern. It should be called Bob's design pattern, right? If you step back and think about it, be like, I think I understand what he's saying. Yeah, this seems to be true. So for the purposes of this lecture, patterns are organized into 2 ways. They have what the pattern does, whether it makes something new, whether it provides some sort of a structure, or it has a certain type of behavior, and it has a scope, whether it's so-called a class pattern, right? These patterns deal with relationships between classes and subclasses, or an object pattern with it before instantiation or after instantiation, basically. So one is more abstract than the other. And there is a problem you saw a few slides ago, there are these really thick books on design patterns, like that first book. I think it's like 500 pages or something like that. I think I have a copy of that book and I always wanted to read it, but I never got around to it. I said, Bob, you have to read that book. One of the challenges with design patterns is there are many, many of them. Does anybody buy a UML book besides me? Did anybody buy a UML book ever? Nobody ever? I'm the only one. If you buy a UML book, you'll notice a similar thing. There are like 100 different UML diagrams. And it's the same with design patterns, but in reality, only maybe 5 to 10 are very popular and really maybe stand out in terms of popularity. So we're not gonna go into all the patterns. We're gonna maybe pick a few that are very popular and talk about those a little bit, but we're not gonna go into 100 different design patterns. How many patterns do you need to know? I don't know the answer to that question, actually. I think it's good to just know that there are 100 of them, and it's good to have a reference book handy when you need to look for a pattern, right? That's my opinion. I'm not very good at memorizing things. My brain is designed for like solving problems and problem solving and analytics. It doesn't seem to be meant for memorization. But here are some of the popular design patterns: adapter, factory, observer, strategy, builder, state, singleton, and MVC. So here's a little kind of organization of design patterns, right? The creator patterns or the factory patterns, the behavior patterns, and the structural patterns. And you can see there are already kind of a lot there. I don't think this is all the patterns, but it's a kind of organization. Here's another organization of patterns, right? We mentioned the 3 categories: creational, structural, and behavioral, the same 3 categories. And then the other dimension or the other axis is the class versus object dimension. So you can see there are already a lot here. This is not all of them. So here are some of the creational patterns, the abstract factory. So the abstract factory, basically it outsources constructors. My favorite example with this one is Tetris. Imagine you are writing Tetris as a game, right? Every second or every few seconds a new block has to appear at the top and it has a different shape. Well, you could set up an abstract factory class to outsource the creation of those shapes. So a factory class that just says get next shape, and then the factory class is responsible for figuring out the next randomly assigned shape to provide to the canvas. So there are many variations on this theme. They're all variations on this basic theme. The Singleton is kind of a special in that that's not exactly a variation. That's responsible for making sure that there is only one instance of an object, a special object, and that there aren't more than one. There are adapter classes, and they're all kind of adaptations, no pun intended, of the adapter concept. So to provide some sort of interface between two otherwise incompatible objects. The example I like to think of there, can anybody think of an example of an adapter pattern? The example I like to think of there is networks and protocols, right? If you take a networks class, the whole class is about adapter patterns and protocols. So ways to communicate, a priori communication mechanisms and interfaces, right? Those are adapter patterns. And then there are several variations. I don't know all of these different patterns in detail. There are behavioral patterns. A chain of responsibility, for example, to give more than one object the chance to handle a request. And interpreter behaviors, iterator behaviors, mediator behaviors, and then several more variations on different kinds of behaviors, the way a piece of software is supposed to behave. A very popular one is a finite state machine, by the way. So allow an object to alter its behavior when its internal state changes. So a finite state machine is definitely a design pattern. Whether or not it's a popular design pattern is a different question. That's a little overview of the different design patterns and how they're organized. And there are lots of resources on design patterns, right? In this lecture, we're going to talk about some of the resources available to you in order to study these. So one of the most popular ones is called the Singleton. Create a one-of-a-kind object for which there is only one instance. Can anybody think of a good example of when we might want to use a singleton? Name?
Joe.
Joe? What do you think, Joe?
The state of something, so a game state, or a board, something like that. I think this needs to be only one.
That's a good example. Joe said anything that needs to keep track of its states, right? If you have multiple copies of a state, then the states get inconsistent. That's, if I understand your answer correctly. That's a good example. That's not the one I was thinking of, but it is a very good example. There's one that's even more exciting. Anybody think of I think that you've all kind of run into this problem before somehow, in some way, shape, or form. Singleton design pattern. A good example relates back to that very generic design pattern that I described at the beginning, the 4 components, the GUI, the processing, the data, and the output subsystems. The Singleton pattern is very good to use in the case of the data access. Imagine you have a database, and the database is 30 gigabytes or 30 terabytes. Imagine if you accidentally created a copy of the database and turned like 30 terabytes into 60 terabytes or something. That would not be good, right? So that's a good time to use the Singleton pattern, is when you have large data sets. It sounds simple, and it is simple on a conceptual level. Right? Sometimes we just want a single instance of a class to exist in the system. We want just one window manager, for example, or one printer, or one, oh, there it is, one database, and one game board. And so then the question is, how do we make sure that there is only one of these instantiated at any time? Because they're tight. We provide, we create a Singleton pattern, and we provide only a single point of access to it. We need to have one instance easily accessible, and we want to ensure additional instances of the class are not created. So a common way to think about this is, oh, let's just have one global variable, maybe it's static, and make sure that it never gets copied, right? This is a solution, right? To have one global static copy of some class, right? A database, for example. Can anybody think of a problem with that solution? It's related to one of the guidelines, which is avoid static methods and variables, if you can. Anybody think of is it Emily?
Yeah. Usually global variables need to be avoided just because they ruin they don't follow like object-oriented patterns essentially. Like they don't, because obviously anything can access it, so it kind of just ruins design.
That's right. You get one from being such a good sport. Sorry, that was a bad throw. So Emily said, well, she said a few things, but the thing that she said that I liked the most was anyone can access a global variable or a static method, right? And therefore, imagine you have a piece of software with 1,000 classes or 1,000 objects. Do you really want all 1,000 objects to be able to access that database, for example, or that thing? The reason we want to have simplified patterns of communication is that means one small change could break everything. And it really, we don't want that. We want to be able to make changes to for example, our database by defining an interface to the database. Anybody can use that interface, but the details of what happens underneath, behind the interface, can change without breaking everything. And with static global variables, everybody can communicate with that, and possibly making changes can have drastic consequences. Right? Imagine the case where somebody's trying to modify and enhance the performance of a web server. Right? Imagine if every time a web server was modified, it broke your web browser. That would be a nightmare, right? So there are well-defined communication protocols to decouple the two pieces of software so they can communicate reliably. I can make changes to my client without breaking anything, and someone else can make changes to the server without breaking anything. I'm rambling a little bit there. So here's a solution, right? Here's the static variable to hold a single instance. And we have a method called getInstance, right? It's in the Singleton class. And if it's not been instantiated yet, we create a new one. But if it has been instantiated, we return it. So that's a kind of solution. Right, here's what that looks like in UML notation. Right? And by the way, somebody asked me in an email, how do you tell the difference between member variables and methods in a class diagram? Well, this is a good example, right? Here's a line that separates the member variables from the methods, right? So that's how you do that in a class diagram. Right, there could be concurrency challenges, right? In any multi-threading application, there could be concurrency challenges. Does anybody know how that could be addressed in Java, by the way? That method? So imagine two different objects call getInstance at the same time, right? That could cause problems, theoretically. Anybody know how that could be addressed in Java application? Name? Chayao. What do you think? Threading, multi-threading, but there's a keyword in Java too. Synchronize. Very good. Very good. You use the synchronize keyword, and I think you add it right here. Pretty sure. And therefore, that method can be only accessed by one thread at a time. That's the idea. Yeah, and you know, you have to test it out. Obviously, maybe there's some information that's not available at the time that it's instantiated that it requires, but of course there are solutions to that. Okay, then we have this object creation patterns, the factory patterns. We create objects without exposing the creation logic to the client and refer to newly created objects using a common interface. This is for programs that need to instantiate a lot of objects, right? Like a factory. So that's at least this one has an intuitive name. And for some reason, I always think of the Tetris game. But I'm sure, you know, there are lots of other examples as well. Any game pretty much has this pattern in it, right? In games, you're like somebody that's like has adversaries, right? And you are encountering different adversaries constantly, right? You might be like shooting them down or something. So it's good to have the factory pattern to generate. Or in Donkey Kong, right? In Donkey Kong, you need to keep generating those barrels. Right? So games are a good example of when you need the factory pattern. Creational patterns which abstract and encapsulate the object instantiation process. Usually that constructor is very simple, right? But when you have a scenario where you're trying to create a variety of different objects and you don't want some complex constructor, you can outsource all the complexity to its own factory pattern. Factory patterns hide how objects are created and service the system independent of how its objects are created. Class creational patterns focus on the use of inheritance to decide the object to be instantiated in the factory pattern. The factory method pattern can save you from those awkward dependencies in object-oriented design by letting you define an interface for creating an object, but let its related subclasses decide which classes to instantiate. I wish I had known about this pattern when I was an undergrad. I didn't know about this when I was an undergrad student. Here's the representation in UML. By the way, I also struggle with UML diagrams. If they get too fancy, I start to get lost, which is why I have a UML book. I have one in my office that I look at if I need to. And we can have different variations on the factory theme, right? Concrete factories, abstract factories. Here's an example represented in UML, right? An abstract factory. And there are two methods in the abstract factory: create product A, create product B, right? And then we have a concrete factory object that overrides or has its own implementations of the same two methods, concrete factory 2. So this is a kind of hierarchy, right? This is a class hierarchy right here. And then we have a client class that collaborates with the abstract factory or is associated and asks for products, right? The client asks for a copy of product A and a copy of product B, and the abstract product A decides which concrete product it's going to produce, right? And here we see the client requesting an abstract product A or an abstract product B. So this is a schematic representation of this factory pattern. It doesn't really help very much. Another good example is the shape. So in the drawing editor example, you need to create different shapes, right? And they have different numbers of edges. So here we have a program called Factory Pattern Demo, right, with the main. And by the way, I've put some hints here. The filled diamonds mean composition, and then the empty diamonds mean aggregation. So a shape factory is composed of, right, the factory, the pattern, factory demo pattern. We have a method called getShape, right, and then it takes a string that specifies what kind of shape we want to create. So we just call getShape, and then we say, okay, what do we want, a circle or a rectangle? And then we pass that to the draw interface, and then if it's a circle, then we return a circle. If it's a rectangle specified in the string, then we return a rectangle. It's not a very exciting example, but this would be more exciting if there were like 10 different shapes, right? Then it would be more interesting. Okay, I suggest we take a 10-minute break before we continue on with design patterns.